Hello, dear students. Welcome to the class, welcome to the channel, and welcome to this playlist in which we are discussing about the instrumentation and sensors. In very previous class, we have discussed about different type of sensors. We have discussed about all these kind of sensors uh, based on pressure, force, temperature, flow, and many more. Displacement. You can name any physical quantity. Last last type of sensors we've discussed about was optical sensors, and I've told you to revise it from home. So if you want to check out the previous video, you can click on the I button. The link will be flashing on the top right hand side corner of your screen. You can click on it and you can watch that video. Today, in continuation to that, we are going to discuss about different type of transducers and sensors, and if time permits, then we will also talk about the instrumentation as well. So the first sensor for today is the ultrasonic transducer, and we all are familiar with ultrasonic in our cars for the parking or in sonar as well, right? So it's used in so many fields. It has a it has very wide horizon of application, especially for fluid measurement or fluid flow rate measurement, liquid level, and translational displacement. So it has very wide range of applications. And what ultrasound or ultrasonic basically is, so ultrasound is a band of frequency in the range above 20 kilohertz, which means that is above the sonic range that humans can usually hear, so you cannot hear the ultrasonic sound. And the measurement devices that are used are ultrasound that consist of one device that transmits an ultrasound wave and another device that receives the wave. So the changes in the measured variable are determined either by measuring the change in time taken for the ultrasound wave to travel between the transmitter and receiver, or alternatively by measuring the change in the phase or the frequency of the transmitted wave. Now, the most common form of ultrasonic elements are piezoelectric crystal. So we have discussed about the quartz crystal last time. That is very much similar to this one, which contained in the casing, as you can see in this image. Sorry, as you can see in this image, this is an ultrasonic sensor. So such elements can operate interchangeably as either transmitter or receiver, and these are available with different operating frequencies, which varies between 15 megahertz, between 20 kilohertz to 15 megahertz. And the principle by which the operation takes place, so that is very basic, right? We have seen it already in physics in the first or second sem. So it's same as the piezoelectric transducer. So even if you still want me to discuss about it, we can discuss about it. Just mention that in the comment section below, we will discuss. And for completeness, we should also mention the capacitive ultrasonic element as well, which consists of a thin dielectric membrane between two conducting layers, and that membrane is stretched across the backplate, and big voltage is applied. And when a varying voltage is applied to the element, it behaves as an ultrasonic transmitter, and ultrasound wave is produced. So the system also works in the reverse direction as an ultrasonic receiver, and elements with resonant frequencies in the range between 30 kilohertz to 3 megahertz can be obtained. Then the transmission speed of this ultrasound varies according to the medium through which it travels. So the transmission speed for some common uh, media are as this table. You can see for air it is 331.6 meter per second, for water 1440, wood 3320, and so on. So when transmitted through the air, the speed of the ultrasound is affected by environmental factors like temperature, humidity, air turbulence, and the temperature has the largest effect on this quantity. So the velocity of the sound through the air varies with the temperature according to the V equal to 331.6 plus zero point 0.6 into T meter per second. So it's not very much relevant, so we are not going to discuss in detail. But let me quickly give you a glimpse of relationship between wavelength, frequency, and directionality of the ultrasound waves. So you all must have learned about the de Broglie's principle. Lambda is equals to V by F. Lambda is wavelength, V is velocity, and F is the frequency of the ultrasound waves, which shows the relationship between lambda and F, which depends on the velocity of the ultrasound, and hence it varies accordingly to the nature of the temperature of your medium through which my wavelength or my wave is traveling. And if you want to check out the nominal frequency wavelengths, you can check out in the table here. Nominal frequency wavelength in the air is this, and the cone angle of the transmission varies this much, so you can check that out as well. And this is something we are meant to discuss, that ultrasound as a range sensor. So as we know, the basic principle of ultrasonic range sensor are to measure the time between the transmission of the burst of ultrasonic energy from ultrasonic transmitter and receive of the energy by ultrasonic receiver. Then we will calculate the distance, which will be d equals to vt, where v is the ultrasound velocity, t is the measured energy transmit time, and an obvious difficulty in applying this equation is the variability of v with temperature according to the equation which we discussed above. So how do you solve this problem? So there are multiple ways to solve this problem. One solution to this problem is to include an extra ultrasonic transmitter receiver pair in measurement system, in which the two elements are positioned a known distance apart. So the measurement of the transmission time of energy between these fixed pair provides the necessary measurement of velocity and hence comparison for any environment temperature changes. Then the degree of the directionality in the ultrasonic element used for range measurement is unimportant as long as the receiver and transmitter are positioned carefully so as to face each other exactly, like the normal line to their faces are co-inclined or coincident. Thus, the directionality imposes no restriction on the type of element suited for the range measurement, but the element choices is restricted by the attenuation characteristics of different type of element, and relatively low frequency elements have to be used for the measurement of the large range. Then we have the different resolution and accuracy of these sensors. We are not going to discuss that in detail right now. We can use the ultrasound for 3D object motion detection. So that is one of its uses. But the one thing which we should discuss is how the noise affects the ultrasonic measurement. So the signal levels at the output of the ultrasonic measurement system are usually of low amplitude, and because of that they are prone to contamination of electromagnetic noise, and that makes it necessary to use special precautions like the grounding of uh, making ground lines thick right? Making grounding thick, using shield cables for transmission of the signal from ultrasonic receiver, and locating the signal amplifier as close to the receiver as possible. Then another potentially serious form of noise is background ultrasonic produced by manufacturing operation in the typical industrial environment that many ultrasonic range measurement system operate. Then the analysis of the industrial environment has shown that ultrasound at frequencies up to 100 kilohertz, it is generated by the many operations, and some operations generate ultrasound at higher frequencies up to 200 kilohertz as well. So there is not usually any problem in ultrasonic measurement system operated at frequency above 200 kilohertz, but those often have insufficient range for the needs of the measurement situation. And in such circumstances, what do we do? Any object that are likely to generate energy at ultrasonic frequencies should be covered in the sound absorbing material. Any sound absorbing material that interfaces with ultrasonic measurement system is minimized. And the placement of this sound absorbing material around the path that measurement of ultrasound wave travels along contributes further towards the reducing the effect of the background noise. What is the natural solution? So natural solution is partially provided by the fact that the same process of distance traveled and absorption that attenuate the amplitude of ultrasound wave traveling between the transmitter and receiver in the measurement system also attenuates the ultrasound noise that is generated by the manufacturing operations. Now, because this ultrasonic energy is emitted at angles other than the direction that is normal to the face of the transmitting element, the problem arises in the respect of energy that is reflected of some object in the environment around the measurement system and back into the ultrasonic receiver as well. So that is no longer path that direct one between the transmitter and receiver and can cause erroneous measurement in some circumstances. So one solution to this is to arrange for the transmission time counter to stop as soon as the receiver first detects the ultrasound waves, and it will usually be the wave that has traveled along the direct path, and so no measurement error is caused rate as long as the rate at which ultrasound pulses are emitted is such that the next burst isn't emit unit all reflections from previous pulses have died down. So in circumstances where all the direct path becomes obstructed by some obstacle, the counter will only be stopped when the reflected signal is detected by the receiver, which gives potential large measurement error. So this is the Doppler shift. We are not going to discuss this, Doppler shift. And then we have the ultrasonic imaging. So it's not used very much in general, but in medical diagnosis and sometimes in military purposes it is used, and in sometimes in industrial testing procedures ultrasonic imaging is also used. And all these applications, a short burst of ultrasonic energy is transmitted from the ultrasonic element into the medium being investigated, and the energy that is reflected back to the element is analyzed, right? And the frequency it ranges from 1 megahertz to 15 megahertz. Now the ultrasound which is reflected back at all interfaces between different materials, with the proportion of energy reflected being a function of the material either side of the interface. So the principal component inside the human bodies are water, fat, muscle, bone, and the interfaces between each of these have different reflectance characteristics. So the measurement of the time between energy transmission and receipt of the reflected signal gives the depth of the interface according to that equation which we studied earlier. Remember 13.5, let me take you there. This one, D equal to VT. So because of that, in medical diagnosis procedure, the reflected energy appears as a series of peaks with the magnitude of each peak corresponding to the type of interface that is reflected from, and the time of each peak corresponding to the depth of the interface in the body. Thus, the map of fat, muscle, and bone in the body is obtained, and fuller account can be found. Full account can found elsewhere, right? Then the other application in the industrial test procedures usually involve detecting internal flaws within the components, and that flaws can cause an interface between air and the material that the component is made of. And by timing the reflection of ultrasound from the flaw, the depth of each flaw can be determined. Then we have the big guns, the nuclear sensors, and of course, nuclear sensors are uncommon measurement devices because you won't find a nuclear, uh, nuclearly active, nuclearly active matter or nuclearly active quantity at your house. So they are uncommon measurement devices partly because the strict safety regulations that government uses, and partly because they are usually very expensive. So some very low level radiation sources are now available that largely overcome the safety problems, but measurement are the prone to contamination by background radiation. And the principle of operation of nuclear sensor is very similar to the optical sensor, is in that radiation is transmitted between a source and the detector through some medium in which the magnitude of transmission is attenuated according to the value of the measured variable. So Caesium 137 is commonly used as a gamma ray source, and a sodium iodine device is commonly used as a gamma ray detector. The sodium iodine gives voltage output that is proportional to the radiation incident upon it, and one current use of nuclear sensor is a non-invasive technique for measuring the level of liquid in the storage tank, and also they are used in the mass flow rate measurement and medical scanning applications as well, right? But nuclear sensors are often rare. Then we have the micro sensors in the last. So micro sensors are millimeter sized 2 and 3 dimensional micro machineries or micro machine structures that have small size and improved performance. They have better reliability and lower production cost that many alternative forms of the sensor. And currently the devices to measure temperature, pressure, force, acceleration, humidity, magnetic field, radiation, chemical parameters are either in production or at the advanced stage of research. So these micro sensors are usually constructed from silicon semiconductor material, but sometimes fabricated from other materials like metal or plastic or polymer, glasses, and even ceramic. And then they are deposited on a silicon base. So silicon is an ideal material for the sensor construction because it is excellent mechanical because it holds excellent mechanical properties. So its tensile strength and Young's modulus is comparable to the steel, and whilst its density is less than the aluminum. So sensors made from a single crystal of silicon remains elastic almost through the breaking point, and mechanical hysteresis is very small. And in addition, the silicon has very low coefficient of thermal expansion and can be exposed to extremeness of the temperature and most gases, solvent and acids without deterioration. So these micro engineering techniques are essentially enabling the technology for microsensors, which are designed so that the electromechanical properties change in response to the change in the measured parameters. Then many of the techniques used for the integrated circuit manufacturers are also used in sensor fabrication. Common techniques being growing and polishing, then thin film deposition, ion implantation, wet and dry chemical and laser etching, and photolithography. But apart from standard IC production techniques, some special techniques are also needed in addition to produce the 3D structures that are unique in some type of microsensors. So the various manufacturing techniques are used to form sensors directly in silicon crystal and films. And typical structures have forms such as thin diaphragm, um, cantilever beams, and bridges. And the small size of the microsensor is the particular benefit in many applications. It also leads to some problems that require specific attention as well. For example, microsensors typically have very low capacitance, which makes output signal very prone to noise contamination. And because of it, it is usually necessary to integrate microelectric circuit that performs signal processing in the device. And because of that, it becomes smart microsensor. Then another one of the problems is microsensors generally produce output signals of very low magnitude, which requires the system types of analog to digital converter that can cope with such low amplitude input signal. It gets solved by using sigma delta conversion. So if you want to know about sigma delta conversion, just mention it in the comment section below. I will make a video on it separately. This is based on the charge balancing techniques and gives better than 16-bit accuracy and is less than 20 millisecond, right? So special design can reduce conversion time to less than zero point 0.1 microsecond if necessary. Right now almost all the microsensors have analog output, but resonant technology pressure measuring device is now available with the digital output as well. This consists of silicon crystal on which two H-shaped resonators are formed, one at the center and one at the edge. And if the pressure to be measured is applied at the crystal, the central resonator is compressed, and changing the it will change the spring constant of the material, and thus it will reduce the resonant frequency. At the same time, outer resonant is stretched, which will increase the resonant frequency. Then it will result in frequency differences produces a digital output signal that will be proportional to the applied pressure, and the device can also be give signal proportional to the differential pressure if this is applied between the center and the periphery of the crystal. So microsensors are most commonly used for pressure, acceleration, force, chemical parameters, and they are widely used in medical applications for blood pressure measurement to the temperature measurement of body and so on. The mechanical microsensors transform measured variables such as force, pressure, and acceleration into displacement. The displacement is usually measured by capacitive or piezoresistive techniques. Although some devices use the technologies such as resonant frequency verification, resistance change, inductance change, the piezoelectric effect, and changes the magnitude or optical coupling. So the design of the cantilever silicon micro accelerometer is shown here in the image, and the proof mass within this is about 100 micrometer across, and the typical deflection measured is of the order of 1 micron. Then an alternative capacitive microaccelerometer provides a calibration, compensated and amplified output. It has capacitive silicon microsensor to measure displacement of the proof mass, and this is integrated with a signal processing chip and protected by a plastic enclosure, as you can see here. So the capacitive element has 3D structure, which gives a higher measurement of sensitivity that surface machined elements. And microsensors to measure many other physical variables are either in production or at an advanced stage of research, as I've said. Like sensor measuring magnetic fields are based on the number of alternative technologies like Hall effect, magnetohysteresis, magnetoresistors, magnetodiodes, magnetotransistors, etc. Then the radiation microsensors are made from silicon PN diodes or avalanche photodiodes, and they can detect the radiation over wavelengths from visible spectrum to infrared. Then we have the microsensors in the form of the microthermistors, a PN thermodiode, or then we have thermotransistors, which are used as a digital thermometers as well these days, and about which we are going to discuss in the upcoming lectures in detail as well. They have also enabled the measurement techniques that were previously labeled laboratory based ones, and to be extended into the fields of instruments, right? And examples are spectroscopic instrumentation and devices to measure the viscosity as well. So we'll keep today's class till here. If you have any doubts, any queries, any questions, please feel free to mention them in this comment section below. If you have any feedback related to channel, or if you want me to make videos on some specific topic, please mention that in the comment section below as well. I will be seeing you next time. Thank you very much for listening. Goodbye for now.